When we look at trigonometric integrals, much of our work is going to be identifying patterns and then acting according to what we see. Here we have the integral of the sine cubed of theta times the cosine to the fourth of theta d theta. Some of what I'm going to present to you through this section of videos may not make sense right away, but it'll come together at some point. Right now, what I'd like to point out is that we have an odd power on the sine function. When we have such a situation, what we will end up doing is breaking apart the sine powers. So we have the sine cubed of theta. We're going to think about that as the sine squared of theta times the sine of theta. Further, that trig function that has the odd power, we're going to identify that as our du, thinking about a u substitution. And so we're going to identify that du is equal to the sine of theta d theta. If that's the case, it would follow by an antiderivative that u is equal to the negative cosine of theta, but I'd rather not think of it that way personally. You can if you like. What I'd like to do is identify, kind of working backwards, u is the cosine of theta, therefore du would be the negative sine of theta d theta. Then by multiplying in our integrand and dividing by negative 1, we can see that we have in our integrand negative sine of theta d theta, and that's going to become our du. Let's rewrite what we have so far. I've got the integral of negative sine squared of theta times the cosine to the fourth of theta times the negative sine of theta d theta. At this point, it may look like it's worse. It looks worse. We started out with a nice tidy sine cubed of theta cosine to the fourth of theta d theta. Now we have a negative sine squared of theta. We have a negative sine of theta. Cosine to the fourth of theta is still present, and we have a d theta. We not only have more factors, but we have now two minus signs running around. This we'll fix it shortly. Recall that we have a Pythagorean identity that states that the cosine squared of theta plus the sine squared of theta is equal to 1. This means that we can rearrange the equation. Sine squared of theta equals 1 minus the cosine squared of theta. The point of reminding you of that is that we're going to replace the sine squared of theta, and in fact this time we're going to replace the negative sine squared of theta. Because there's a negative in front of the sine squared of theta, instead of writing 1 minus cosine squared of theta, I'm going to replace that by cosine squared of theta minus 1. That replaces the negative sine squared of theta, and then I'll just write the rest of the integrand as it was. Times the cosine to the fourth of theta times the negative sine of theta d theta. Now we have that negative sine of theta d theta is our du, and all of the other instances of trigonometric functions are cosine of theta, or cosine of theta to a power. Let's simplify the integrand and see what happens. When I say simplify, I mean distribute the cosine to the fourth of theta. We end up with the cosine to the sixth of theta minus the cosine to the fourth of theta times the negative sine of theta d theta. Essentially, at this point, what we have is the integral of u to the sixth minus u to the fourth du. Being able to write it this way was the point of everything that we've done. That is, identifying which trigonometric function had the odd power and making that our du, and then converting all other instances of that trig function into the other one. At this point, since our integral looks like u to the sixth minus u to the fourth du, we're going to integrate using the power rule. We end up with 1/7 times the cosine to the seventh of theta minus 1/5 times the cosine to the fifth of theta plus c.